whenever there is a claim concerning a population, and the population may not necessarily be a population of people, it can be anything, it can be insects or what have you. Okay, then we may need to do a test to really decide whether to accept such a hypothesis or not. So, for example, there may be a claim that, okay, let me take a simple example, like let's say delivery service on campus. So there may be some delivery service, and they tell you that, well, if you order something and you send it through us, maybe it takes on average 10 minutes for us to reach you. Now, how do we test such a claim? Okay, because you can't just decide if you now order something from them and it takes 30 minutes. Okay, the tendency is that maybe the advert, what they are saying is not true, but it's possible that somebody will also order something and it comes in 5 minutes. Okay, so for us to be able to make an informed decision, we need to do what we call a test of hypothesis. Okay, so because they are talking about average, what we will use is a sample average. Okay, but when we calculate a sample average, we cannot just say that, okay, the sample average is 15, so the company is not telling us the truth, or they are underestimating their average delivery time, because that's just an average. It's a descriptive statistic, so you can't use descriptive statistics to make conclusions concerning a population. You need to move a step further to do a test of hypothesis. So the first one we talk about is where you have one sample, and here I'm talking about an average, right? So test of, in this case, averages, test concerning averages. Okay, so the first one we'll talk about is when you have one sample. Okay, so I have one sample and there is a claim concerning this sample. So usually we use what we call the t-test, right? Or it may be a z-test depending on the sample size you have. Okay, so in R, what we will use to do it is called a t-test, okay? So let's look at this, t.test. So I will say 1 and 2 samples, right? Because I will talk about 1 and 2. Okay, 1 and 2 sample test. Okay, so we use just one a function called t.test. So if you come here, I'm assuming that we all have done statistics and we understand some of these things. But the simple explanation is that we may have one sample, or sometimes, you see, we look at the anorexia data, right? There is pre and post weight. So later on, we'll be checking whether the intervention is successful. If it is successful, we expect their post weight to be larger than the pre weight because we want them to gain weight. So if it is different, it must be larger. Then we say this is, yeah. So this test can do two it can be one sample or two samples. You have to bring it down. Other than that, those that have played, they won't see. Now, so if you look over here, there is t-test, right? It says it performs what? 1 and what? 2 sample t-test, right? On vector data. We have to switch this off. We have to do off. I think it's the second one. Second one from the top. I think so. Okay. So if you want to do a t-test, then for the one sample, it means maybe I have think it should be in the back. Okay. So it means that I'll have a sample. For example, if I asked all of you to order something, and then we use that delivery company, maybe is it Global or Jumia or whatever you know. Your staff may come 20 minutes time, the next person maybe 10, the next person 5, the next person maybe 8, and so forth. So we have that, and then now we want to check. We want to, please can you see? This is better. Okay, all right. Okay. So it means that we have to check, then yeah, it should be in the back. Okay. So we have to check whether okay, so if you in basic statistics you say you have a H naught, right? You state a hypothesis, something like that. Okay. Then I have to draw in, so it won't be so nice. I'm using the map. Okay, so we have this, right? Sorry. It's 10, right? Sorry. 10 minutes. Okay. So in the population, what we are saying is that the average delivery time is 10 minutes. It means if we order, or since the company came to in existence, all their deliveries within, if we add all of them, divide by the total number, we are going to get it. Okay, then we take our sample. As I said, maybe the first one, this thing came in maybe 5 minutes. Okay, so we'll have 5. The next one maybe 10 or maybe 12 and so forth. So I'll get a, a whole lot of samples, and these are sample or delivery times, right? So I get something like that and so forth. So the question is, how do I solve this? Of course, I need an H1, but the H1 will depend on how I perceive the problem. So if I believe that they are cheating customers, then what I'm going to say is that their actual delivery time is actually greater than what? 10. Do you agree? Yeah, but they are just stating or underestimating it so that you come to them. So how do I do this in R? Of course, I'll get a data set. So I have my X, which is the sample. In this case, a vector. Then Y, if it is Y by default is null, because I can have one sample. It means there's no Y. Now then the alternative, remember we can have okay, so the alternative hypothesis, we can have so it's not working. Okay, let me just write here. It's not moving. I don't know. Okay, so let me say if I have the alternative, I have this to be mu equal to 10. So there are 3 things that I can do mu not equal to 10. Alternatively, we can check mu greater than 10, and then what? Mu less than 10. So these are the 3 alternative hypotheses we can. So if I think they are cheating customers, I'm going to check that one, right? If I think they are actually underestimating their delivery time, then I'll do that one, right? And then this is for both. if they are either cheating or they are underestimating. So that's it. So when you go to R, you have the same thing. Okay. So there's two-sided. Two-sided is a not equal to. It means I'll reject for very low values or very large values. Then less will be the less than one. It means what they are stating is less, right? And then greater will be the other one. So those are the three things. So at any point, you can only test one, okay? Because you don't state a hypothesis with several alternative hypotheses. It must be one alternative hypothesis. Then also we see mu, okay? So mu is the value of the mu. In this case, it's 10, right? So which by default is 0, we change it to 10. Okay. Then paired. I just talk about the anorexia data. The anorexia data, we take a patient, we weigh you before the program, and then we weigh you after the program. So there's what before and after measurement. Now, in the case of the delivery, if I'm using Global and now I want to use Jumia delivery, then they are independent. Okay, so I can order 10 from Global, I can order 5 from what? Jumia. Is that okay? So those ones, they are independent, but the paired one is where you are before and after measurement. Is that okay? So you bring an intervention, you want to see how, so you measure something before and then after. Okay, that is paired test. So paired is a logical argument. If we say true, it means we are doing a paired thing. If it is false, by default it's false. So it means it is the independent samples. Okay. Then var.equal. Now, when you are considering 2 or more samples, you always remember if you are using a t-test, we assume that it comes from a normal distribution with a constant variance, right? Okay, so you want to check whether you should say that the variances, they are homogeneous or they are not. Okay, so usually you can also test this. I will not do it for you, unlike, let's say, SPSS, which will give you the 2 results. Variance is equal, variance is not equal. I will not do that. You have to do this. Now, how do you do that? You can also test whether the variances are the same, okay, before you move on. Before you move on to do your test. And so then lastly, we have the confidence level. So the confidence level usually is 95%. But of course, you can test for 90 and so forth. So if you want to change it, you come to here, conf level, and then you change and so forth. So now, how do we do some of these tests? Let's copy this and paste here. Okay. We copy and paste here. And then let's take a sample delivery time. So sample delivery. Let's just, so everybody is going to sample observations. Okay, so you sample observations from, let me just do it from a uniform distribution. So I sample, let's say, 20 observations from a uniform distribution that has minimum to be equal to, let's say, 5 minutes, or let me say 3 minutes, and then maximum of, let's say, 30. Okay. So what do I mean by this? I want to, you know, the uniform distribution. You state it by having the parameters as minimum value, A, B. And so the S density function is 1 over what? B minus A. So here, what I've done is a uniform distribution. So if we're all going to get different. So these are my sample times. If I want, I can round it so that I get what? Whole numbers as the delivery time. So I round it and then I do it again. So my sample delivery time are this. So I'm assuming I placed 20, 30 orders. Is it 30? No, 20 orders. And these are my sample. So the first one, it took them 25 minutes to be here. The next one was 19. The next one is 25. The next one is 14. Then 4, 4, and so forth. So your own will be different from mine. So these are the times. Now, how do we test their claim that the average delivery time is what? 10. Is that okay? All right. So what do we do now? So here, let me just add that sample delivery times, delivery time. And here we want to test the hypothesis. Test the null hypothesis. Test H naught. Let me use H naught. That mu is equal to 10 minutes, right? That's what we want to test. So this one, X will be what? The delivery times. Is that okay? X is the delivery time. Do we have Y? No. Okay, so I can delete it or leave it like that because it's null. It doesn't contain any value, right? Okay. Then the alternative, maybe you want to do 2, right? Or maybe let's assume that they are actually underestimating their delivery time. So they are cheating customers. So we say it's greater, right? I delete everything and leave what? Greater. So I'm testing the hypothesis. The hypothesis I'm testing now is this. Okay. So the hypothesis I'm testing now is that H naught is equal to mu is equal to 10, and then H1 is that mu is greater than 10, right? Is that okay? That's what we are testing. So this I'm using greater. Okay, that's why I chose greater. Okay, and mu here should be 10, right? Paired is false. Okay, and I mean you have one sample, so it, I mean the pair cannot be true. And then bad or equal is also false because so is so one sample. Then confidence level, maybe we leave it at 95. Is that okay? Right. So with this, we are good to go now. So I do this, and this is my result. So this is my result. And then now we see how we will interpret it. Okay. So the result shows that this is what? One sample t-test. The data is what? Sample delivery time. Okay. Then the t, remember if we were to do this test, okay, this is the hypothesis. So I have the hypothesis. Then also A is that. Then B, I'll get my test statistic. What is our test statistic for such a test? It's simple. It's T. So it's either T or Z. Okay. Now, if it is a T, it will either be T or Z. It will be x bar minus mu divided by x over root n, right? Here, we are assuming that n is less than 30, right? Or it can be a Z. It can be Z is divided by sigma root n. Here, n is less than 30, sigma unknown. Sigma is not known. Here, we are assuming that n is large, so n is greater than or equal to 30. And here, sigma, if n is greater than 30, then sigma may be known or unknown. Whichever one, it suffices. So if I even have S, so this can be S, but if S is unknown, sigma is unknown, but N is large, I can still approximate it as Z. But whatever it is in R, you still use ZF. So that T is like this. So S bar minus mu is 10 divided by the standard deviation and the number of observations, which is 20. So that's what we have over there, that T. Then degrees of freedom is also N minus 1, right? So you have 19. P-value is this. Remember when we are doing a hypothesis test, there are 3 ways we can make a decision. So one would be that you use your test statistic and then we read from tables, right? Okay, so this one, our rule will be that we reject H not if T is greater than T that we read from tables, N minus 1, N minus 1, okay, alpha, okay. Alternatively, we can also use the p-value. If we will reject if the p-value is greater than, sorry, less than, if the p-value is less than what? Alpha, right? Or we can also construct confidence interval. Okay, interval. So we can also do a confidence interval. So I'm going to show you all these 3 on the plot. Okay, so this T, if you take tables, or remember we talked about probabilities, right? So the quantile for the T distribution is Q, QT. Okay, so if you look at QT there, so here I can also I can compute the test, what you were reading from tables in S, and then we give you those sheets. I can compute it from here as QT, right? The P is 0.95, this one, the QT. So if I want to compare my value with what I'll get from the tables that you were used to, lower the tail through, let me just take this one off. Okay, so the degrees of freedom is 19, right? What about our P? Our P is 0.95, right? So let's see. It's 1.72, right? So if I come here, what am I going to say? Sorry. Remember, this is it, right? This one. Now I have found this to be, okay. So the T that I computed in R, you see your results, T is 1.86, isn't it? Is everybody okay with this? T is 1.96, so I go there. I say T is 1.86. Okay. Then my T that I read from table, T19, 0.95, it gave me what? 1.72. So what is my decision? Since T that I computed from my sample is greater than what? The T that I read from tables, I will reject the null hypothesis. What it means is that they are really underestimating what? The delivery time. Is that okay? Is that okay? So that's it. So that's how you use the T that, but I mean, it means that you have to go and read the other one. So there are other better ways of doing it using another p-value. So the p-value, let's look at the p-value. We compare the p-value with our alpha. Our alpha was 0.05, right? Is that okay? What is the p-value? 0.03 or 0.04. It is less than alpha. So what do? We reject the null hypothesis. That's the same thing we did with the T, isn't it? Is that okay? Okay, so that's one part. And then also this one. We also have a 95 confidence interval. Now, here, we are checking whether our interval encloses the population parameter. The population parameter is 10 minutes. So you check, does our interval enclose this parameter? Does it enclose it? Does it enclose 10 minutes? So this one starts from 10.26 to infinity. Does it enclose our 10 minutes? No. So what do? We reject the null hypothesis. So whichever one you use, you should come to the same conclusion. You can either use a p-value, you can use your test statistics, read its counterpart from tables, okay, and then you conclude, or you use the interval. Is that okay? Okay. So that's the one sample. Then we can also have two samples. So let's look at two samples. So two samples, let's look at the first of all, let's try the anorexia data, right? So let's go to packages, mass, and click on mass. Okay. Then let's look at the health files for anorexia. How many weeks do we have? So the exam, when are you starting your exam? You say, oh, are you sure? It's not 6 weeks. Because we are going to our 9th week, right? For the undergraduate. Yeah. Next week is 24th September. That's when your semester ends. The exam is 24th. Okay, so like 4 weeks. You have like 4 weeks more, right? Or 5. All right. Okay, so we have a bit of time. Okay. All right. So let's move on. I just wanted to know so that okay. So this is what? Data on what? Weight change, right? Is that okay? We've looked at this data before. So it consists of 3: treatment, pre-weight, post-weight. Okay. Now we can display this data in R to see. It looks like that. Okay. Remember, we did some plots concerning this, and we were unable to really check. We can go back and see how it looks like. Box plot. Then we use the anorexia. And remember the first one, the first column is treatment, which is not a. So this is how it looks like, right? Okay. So this is the box plot for pre-weight and post-weight. The question was that, can we say that they've gained weight? Is that okay? When they came and we weighed them, this is the box plot. When they finished the program, these are the box plots for the weight. So can we say that there has been a change, a significant change in their weight? That's what we want to do. Okay. So this is typically a t-test. Can we say that this is paired? It is paired because the same person will take your weight before and after. Is that okay? Is that okay? All right, okay. So here, if you remember your differential classes, it will be that we have our H naught. Okay, we will have mu d equal to 0. What is mu d? Mu d will be that we have a pre-weight, so pre-weight, and then post. So if you take the first person, this is the person's weight before. Maybe this is after. So you find D. D will be what? The difference between this and that. So maybe 3. The next person was 80. Now weighing 85. So 5, and so forth. Okay. So this is what we are going to use our sample. So if there is no change in their weight, we expect mu D to be equal to 0. Is that okay? The average of this should be 0. So then also we have what? 3 cases. Mu d greater than 0, less than 0, or not equal to 0. Okay. So we have to decide. Here, we want to find out whether the weight change is, the program is successful. If the program is successful, we expect them to gain more weight, right? Is that okay? So what will be the difference? Okay. So in what should be our alternative hypothesis? Greater than 0. Yeah. So you see, I will not do this for you. You have to analyze this yourself and be able to tell the program that this is what I want to do. Okay, so let's go back. So now at least we know what we expect. Let's go to help files and let's copy the t-test again. So I copy the t-test again. Okay. Now, what is x? X, we can say is anorexia. And because this is the data frame, we put this one there. It is what? Pre-weight, right? And then y will be what? What will y be? Y will be what? The after, so post-weight. Okay. The alternative, we said it should still be what? Greater, right? Good. So we delete everything. Mu, should mu be equal to 0 or not? Remember what we did over here. Mu d is 0. What we are doing actually is mu d greater than what? 0. So this one, mu will still be 0. Is that okay? If we had said that a successful program is when the person, on average, they gain more than 2 kilos, okay, then in that case, mu d, we will expect our mu d, the average, to be 2. Is that okay? Because now the average of the gain in weight should be at least 2. So we will say mu d is equal to 2, and then our mu d, the alternative will be that it should be greater than 2. So in that case, in now we have to replace what? 0 with 2. Is that okay? So that's how you can change some of these things. Okay. Now paired, what should be the paired should be what? It should be true. Yes. Because we have what before and after payment. var.equal, let's do this. When we finish, we will check this. I'll show you how to check whether you should let var.equal to be true or it should be false. So this is okay for us to do now. Okay. So let's run it. Is everybody okay with this? Is everybody okay? Any question before we move on? Okay. So let's run it. If you have done it, let's run it. We'll get our results again. Now, if you look at it, what do you see? It says now what? Paired t-test. Okay, we took before and after measurements of each. The data, it gives us anorexia and what? A pre-weight, post-weight. So we have our t. So the same 3 scenarios, we can use it. So now remember that this t will compare with a t with what? 0.95 degrees of freedom, 71. But as I said, it's easier to use or the p-value. Look at the p-value. Quite high, right? Can I? The code. So it's just here. Yes, it's okay. Just ask. If you are doing what? Yeah. Okay. Well, it depends. Okay, so yeah, you can because you see before you do that, you want to fit a distribution, and if you fit a distribution, you want to check whether this distribution actually fits the tails, and that's it. That's also can be a test of hypothesis. So it's not only about average. We can check goodness of fit is a hypothesis test. So that you do a goodness of fit test, which is also a hypothesis test. I won't be able, because this is not a statistics class, we won't be able to do all of them. But once you have the basis, you should be in a position to do the rest. So, okay, so is it okay? Can I move on? Can I move on? Okay, so now let's see how we interpret this. Our p-value is 0.99. So what is our decision? We should, what is H naught? What does it mean in practical? There's no difference between, yeah, there's no difference between the average, pre-weight, and post-weight. Okay. So it means we should not reject that. In other words, what can you say about the effectiveness of this regime, the intervention? It was not successful. Is that okay? Because the pre-weight and post-weight, they are not significantly different according to the test. Okay. Now let's look at this. So that's the p-value. What about this one, the 95%? If we are testing our mu d to have what value? Should I go there? What is the value of mu d? H naught is at the 0, right? Okay. So what we need to do is that does our confidence interval include this value? 0. What is the confidence interval? Negative 4.33 to what? Does this include 0? Yes or no? Yes, it includes 0. So what is your decision? So based on this, the confidence interval, what is your decision? We fail to reject the null hypothesis. It's the same thing like you did. So it means there is no difference between the pre-weight and post-weight. If there is a difference, this interval should not include 0. Is that okay? So that's it. Okay. Now let's look at another example where we will have independent theta. Remember, okay, I said I'll talk about var dot equal. We chose false, but what we inform, yes. Yeah, here you say we fail to reject. No, use fail to reject. Yeah, that's yeah. I know that people use accept, but here we don't teach our students to say accept, and there's a reason for it. Because we can also set another same people from the same experiment, and that will lead to a rejection of the null hypothesis. Yeah, so we say we fail, given this evidence, we fail to reject the null hypothesis. And then we reject the null hypothesis. So let's see. See this one, we chose var dot equal to be false. We had no information about the variances. Okay, Ideally, if you want to check this, you must do a test of hypothesis to check whether the variances are the same or not. Okay? Before you, if they are the same, you do that. If not, so to do that, checking for equality of variance. Equality of variance. So there we will not use t-test, but it is called var.test. So var.test, VAR, okay, variance.test. So this is an F test where we are testing whether mu, you see here, what we are doing is to test H naught is that mu1 squared is equal to mu2 squared. Remember, we have pre and post weight. So mu1 is for pre weight, mu2 is for post weight. That's against H1, mu1 squared not equal to mu2 squared. Remember these tests, we use ratios, right? So that's why you have an F test. So we'll have mu1 squared over mu2 squared. Then this should be equal to 1, right? So the next one, this one, it means what? That ratio is not equal to what? 1. So that's the test we are doing now, which is an F test. Okay. Now, so let's do this. Okay. Remember, that test is a ratio test if, so it's the same thing. That's the results. F test to compare or two variances, right? Okay. Now the data has been given. F value is quite small. Remember, in the F test, you only have what? You reject for large values, right? When we do F test, we only reject for large values, not so. Okay. So look at the p-value. At 0.005, will you reject the null hypothesis or fail to reject it? The p-value is 0.0002. Will you reject the null hypothesis of equality of variance or fail to reject it? We reject the null hypothesis. What it means is that the variances are what? Not equal. Is that okay? So if we are computing this, we must put var.equal to be what? False. So actually what we did, we were right to put var.equal to be false. Okay. Look at this one. The 95% interval. Remember, it should include the population parameter. The ratio should be 1 for H not to not be rejected, right? Does this interval include 1? No. So you see the ratio is different from 1. So we reject the null hypothesis of equality. So whether you use your p-value is what? 999. Okay, what is your no, I think you should okay, check this. Is that the same thing you did? Is it the same? Okay, all right. Okay. So whichever one we use, we will get what? The same um, conclusion, whether we use the F. If I go and read for the F distribution, I have the degrees of freedom, they are all 1, 1. So I can even read it. I'll say KF, okay, so I have P, DF1, DF2. So I can say P is equal to 0.95, DF1 is equal to what? 71, right? And then DF2 is equal to what? 71 as well. So I do this 1.48. Then I come to my results and check. Is this value greater than 1.48? No. What I computed from my sample is less than what I read from table. So what do? I fail to reject the null hypothesis. So whichever one you want to use, you can use to make a conclusion. But it's usually easier to use a p-value. Okay. So if you want to do a report and you need to do this test, what you need to do is to copy your f and the p-value. So these values are okay. So you do a narrative that okay, we reject the or we say that the variances are not equal. Okay, then you put this in bracket. Especially when you are writing, like most of the papers you'll be reviewing, nobody will bring all this as a table and present. In some cases, you have the table, but it's actually not necessary because what I've highlighted is enough for you to make a statement and move on. But in a thesis, you may bring the table because there you have freedom to write so much. But in a paper, nobody will, I mean, will allow you at this level to be presenting all this. Okay, so now let's look at some other tests, unless somebody has a question. Other than that, I'll move on to independent tests, where the populations are independent. They don't depend on each other. This one, your pre-weight has influence on your post-weight. So independent true sample test. Okay. So here, let's look at there's a data set called insect sprays. Okay. Insect sprays. Okay. Okay, I'll use this for ANOVA. So let's just look at, let's still use the anorexia data. Here, I want to find out whether those using CBT, their weights are different from those using family treatment. Is that okay? You see, our data contains those who were assigned family treatment, those who were assigned CBT. This one, they are independent. Is that okay? They are, I can even check their pre-weight. So when you go home, you can check. If you take each of them, control, you can do a pairwise t-test to check whether they are, I think the control, there was no difference, but CBT, there was a difference. The difference was significant. Okay, but because we have put all of them together, we did not see in what significant difference between them. But of course, somebody will question when you were assigning them, were you not biased? In other words, did you not, let's say, give all those who are way heavy to the CBT treatment, and all those who weigh maybe less, you gave them to that? So we may want to check whether there are differences between them. So here they are independent. I assign people some, you cannot be receiving CBT and at the same time family treatment. Is that okay? You have to be specific. So here we check the um, okay, we test for variances, not variances. We can do the variance before that. Test for equality of means for what? FT and what? CBT assigned patients. Something like that. Okay. So here, if we want the CBT group, okay, then it means you have to do a bit of like programming to do that. Okay. So maybe I want to say FT. So FT, I'll call anorexia. Okay. Then I want pre-weight. Okay, but see, if I do this, okay, I just get the values for all of them. But what I want is those who were assigned to what? To what? FT. So what do? I need a function within it to tell me that this is FT. Okay, so what do? What I'll do is this. I'll call an erasure. Then I call treat, right? And I want, if I use treat, this one, if I display it, it will display all the, you see, this. Family trees and family trees. So what I'm going to say is that select those equal to what? FT. So if this will be this one, if I do that alone, you see, those that are FT will be true. Those that are not FT will be what? False. Is that okay? Okay. So if I pass this through an erasure pre-weight, it is going to select only those who were assigned what? To family treatment. So you see now, instead of 72, we have what? Only 17 people. Is that okay? Okay. So can you do that for the CBT? So it will be the same thing. The only thing I need to change is what? The only thing I need to change is what? Is what? FT to what? CBT. Good. I must say that this one you can use, some will use subset. There are so many ways to do this. It's up to you to explore. So this one too. So now, if I do this, I have the CBT. Okay. So you see that the CBT groups, they are more than what? They are more than those who were assigned the family treatment. The CBT 25, 26, 27, 28, 29. 29 people were assigned to the CBT group, whereas family treatment, you have only 17. Okay, so now I can do my var.test, right? To see which one is, or if I want, I can do a box plot, first of all. Box plot to see how this data.frame, or I can pass, okay. Let me see data.frame, data.frame, then CBT, and then FT. So let me see how this looks like. Oh, okay. So I can have, it's true. Okay, so I can do, so you see, this is, the first one is the CBT, and then the other one is what? The FT, 2. So if you look at this, will you say they are the same? The CBT group are outliers, right? 2 outliers. Can you see? Very low, very high. So, but other than that, they are virtually the same. But let's do our test. I want to also check in my test, should I say var dot equal is true or not? So I do this test and then I check the outcome. So this one, look at it. The interval encloses what? Encloses 1, isn't it? Yeah. So this one, I cannot reject the null hypothesis. In other words, the variation in what? The CBT group is not significantly different from what? That of the FT group. So in our test, our t-test, we say var or equal is what? Is true. Is that okay? Look at the p-value. The p-value is large, isn't it? There. 0.84, greater than 0.05. So we fail to reject the null hypothesis. And the F value too is small. I'm sure if you read it from tables, you will get a larger value than this one. So that's it. So we have whatever it takes now to be able to do our test. And for that, I go back here and then I copy this and change the things in there. Okay. So instead of anorexia, I'll have what? CBT, right? And then here I'll have what? FT. FT. The alternative, what should be our alternative? Whether they are equal. So two-sided, right? I think it's two-dot-sided. Yeah. Mu. Mu should be 1, no. This one, what we are doing is this. We are finding, we want to check whether the variances are out. Not the variances, whether the it's an independent test. So we have 2, mu1 is equal to mu2, right? So this is the same as stating that mu1 minus mu2 is equal to 0. Is that okay? Is that okay? That's the hypothesis. The other one we are checking is that mu1 minus mu2 is not equal to 0. So mu should still be 0. So mu is 0 paired. Paired is false. Yeah, you are right. So false, we can just write F. That is also accepted. Okay. Var dot equal. It should be true because we found out that there's no difference between them. Okay. Confidence level, we may leave it like that. But remember, if it is an examination, I may say 90%. It means you have to change it. Is that okay? All right. So let's now do our test now and see. So there we look at our results. And if you look at the results here, it says what? 2 sample t-tests. You see now it's no more paired, right? If the variance is the var dot equal is false, it will use a Welch. So it will tell you Welch test. Okay. So data CBT and FT, right? T is this, degrees of freedom is that p-value point. From the p-value, what can we say? There's all. We fail to reject a null hypothesis, meaning it is. Are you sure? Look at it. There's no significant difference between the average weight for those on the family treatment and those on what? The CBT. Which means that at the beginning of the experiment, they were fair to each procedure. Okay. It's not like somebody has given you some bribe, so you assign all the big people to, or those who can eat to that particular one, and then that influences the outcome. The average weights were not significantly different. So that's it. Okay. So that's how we can do a test of hypothesis. 1 sample, 2 samples. Is everybody okay with this? Okay. What you need to do is to practice some of them. But remember that it is not always the case that we'll have only 2 samples, right? In some cases, we'll have more than 2. So if we have more than 2, what do we do? Okay, one may say, well, we can conduct the t-test several times until we make sure that we compare each of them. But that's not good because every test has an associated type 1 and type 2 error. Now, if you do it several times, then you cascade this error. Okay. So there should be an omnibus test, and that leads us to what we call analysis of variance. Okay. So analysis of variance. Analysis of variance. Or what we know as what? ANOVA. Or ANOVA. Okay. Now, so how do we do ANOVA here? Well, so ANOVA is preferred when we have 3 or more populations to consider. Okay. Now, I must say that this is for independent population. Remember that the anorexia data, there can also be a middle post, right? In other words, you check their weight before, then in the middle of the program, you check it again, maybe you check it again, and then lastly, you check it. We call that repeated measures. Okay, so the same way that we have independent tests, you can also have repeated measures. That's for 2 or more measurements, taken on the same thing, the same units. Okay. So how do we do ANOVA? Remember that ANOVA is to help us check several populations. So now let's look at the I said the insect sprays, right? Insect sprays. So let's look at it. Yeah, so please read about it. There's have we installed this package? Is it insurance also? Insurance, the insurance data. Okay, let me see. Okay, so let's explore the insect sprays. What you can do is to do a box plot for it and tell me. So it's about you went to the health house. It says what? The count of insects in an agricultural experiment. Okay, so explore it by doing a box plot of it. How can you do a box plot of it? It says it's a data frame of what? 72 observations on 2 variables. So the variable 1 will tell you the count, and variable 2 is a spray, which is a factor. So how are you going to plot a box plot for this? Have you done it? You got what? But is that what you need to get? So display the data, you will see. If you display the data, insert sprays, it's like this. So you see F, there's a spray, they were named A, B, C, D up to F. So if you take, this is spray A, they sprayed it on, let's say, 12 places. The 12 observation, there were 13 insects that were killed. That one was 14. So if you want a box plot, you want a box plot that will show A, B, C, D up to F. Is that okay? So how are you going to do that? How are you going to do that? All right. So, okay, so if you look at it, it says count and spray. So I'll do a box plot, okay, with count on spray. And my data is what? The data is equal to what? Insect sprays. So this, you can use this to get a nice box plot showing all the categories in this data. There. You can even color it, right? I can choose colors from the rainbow. 6. Then I do it again. So this is what, I'm choosing random colors from the rainbow. So your own may be different. So this is how you can compare them. So if the spray that kills more insects is the better or is the best, the question is which one, if you are giving an advice or consultancy to a company, which of them will you say they should go and buy? Is that okay? So that's a practical situation where you have something like that. Okay. So that's the sort of things we're going to do. There's a package insurance data. Please install that one too. Let's okay. So is everybody okay? What we want to do with the ANOVA? We can use that to answer the question: which spray is the best? Is that okay? Is it okay? Okay. If you do if you install the insurance claims, there's some insurance claims in Midwestern US, so and so. Okay. Now, it calls auto claims, right? So it's a data frame with what? 6,007 observations on 5 variables. So these are some of the data that later on when you are doing your thesis, these are real data that you can use, okay, without the need of going to get other. So if you look at this one, code 0 to 17 use randomly assigned to an individual state, a factor of this. So I may be interested in checking whether the claims from the various states are the same, right? The average claims. So that falls into what we are doing. There are 17 states. Okay, so if you have a state in which you are paying so much claims, will you want to be there or not? So when you finish, you do some, or maybe the rating class. The rating class is quite large. So when we finish, we can also do a box plot. It's a box plot of, let me see, paid as a function of, okay, so let me first do my data. Data is equal to auto claim. Have I auto claims? I think I need to check insurance data. I haven't. Yeah, that's why. So the data is auto claims and then paid as a function of state, I think. States. So let me see. So let's see how this looks like. Oh, auto claims not found. I have to attach it. Data auto. So why didn't it come? Let me do it again. Okay. So data there. So have you seen? These are claims per state. And look at it. I have 17 states, so it won't, if I display this like this. Okay, so still it takes some of the states out, right? Yes. I said it's in the package insurance data. So you have to install package insurance data before you have access to this. But what do I want to, yes. The what? Yeah, so start once you do install, it will come insurance data. Then you select. What do I want to show? Simple. That we can use this to check. So if you look at this, first comment is that there are so many outliers. There are some states which are very large outliers, right? Look at this one. And so forth. But every state except this state, the rest all have what? Outliers. And you see, this one, the plots are not so good because you can't label them. Of course, you can label them on your own by slanting them. Okay, but I can't be doing this in class. It's up to you to be able to explore some of these things. Now, what you can use to do is a ggplot tool if you learn. That will be easier because it will do it quite nicely for you. And so for what I can teach you is a base one, but you can build upon it on your own. We don't have much time to be doing this. But if I want to see each state, it means I have to suppress these axes. In other words, I'll say x axis, x to x axt to be equal to n. So it will not plot any axis, and then I now give it an axis. Okay, or I can give axis take, or I can give labels, and in this case, their labels will be a vector corresponding to each of these axis takes, right? Each of these, I have to use them axis takes. But what I'll do is that I'll write the state in, let's say, 45 degrees so that you slant it and everybody will see what state it is. That's a nice horizontal, so you won't see all of them. Okay. So essentially, to be able to compare several populations, the box plot comes in handy. It helps you to know how they are and what you can talk about it as well in terms of descriptives. And so if we are doing some work on this, you can now talk about them that most of the states, with the exception of one, has what? Outliers. And so, okay. So let's get back to R and see how this will be done. What we want to do is to check whether the averages for what? What do we call it? The insect sprays, they are the same. Once you are done, you can also check for what? The auto claims. Is that okay? So let's see. So ANOVA in R. So there are so many ways to do an analysis of variance in R. What I'll use is AOV, function AOV. It's an analysis of variance. But there's ANOVA and LM. You can use LM as well. So it says what? It fits what? An analysis of variance model, right? Okay. So we are going to see how this is done. So AOV needs a formula, it needs a data. That's okay. Those two are okay for us to go. Okay. So I'll copy that. The formula is usually a linear model. Data is a data frame, okay, in which the variable specified in the formula will be found. So let's see. The first one, we are going to fit ANOVA for insert, right? Insert. So let me say that's how I have named my own. So I need this AOV. Then the formula, first of all, I need the data. What is the data? The data is what? Insert sprays, right? Insert sprays. Then the formula, what I need to do is that I am using or count on what? On spray. Was that the case? Spray. If the spelling is not right, it won't work. Let this be ANOVA.insert. So now I do this. So I have my ANOVA. Then for me to be able to get the results, of course, I can display the results like this, but it doesn't give me much information than when I use summary. So from here I use summary, ANOVA insert, and then we have it. So now we are going to learn how to interpret this. Remember, for any hypothesis test, you are safe to go with what? The p-values, right? So you remember an ANOVA table, this is what we have over here. The only thing that is missing are the total. Okay, but this is an ANOVA table. So this is our treatment, which is the spray, right? Okay. So the degrees of freedom, how many sprays do we have? How many? 6, yeah. So this one, if you look at an ANOVA table, that will be K minus 1, the number of groups minus 1. So that's why we have 5. Then we have 72. So this one is what? 72 minus 6. And that is n minus k. N minus what? The number of groups. That's why we have 66. If we are the total will be 5 plus that, which is 71, which is n minus 1. Is that okay? Then you have sum of squares. Okay. Then you have mean squares, which is what? The sum of squares divided by the degrees of freedom. Right? And then you have F. F is what? The mean square treatment divided by what? The mean square error. That gives you what? 34.7. And so forth. Remember, in the in basis or statistical inference, you compare this value with what? The table one, right? Which is that we read from F distribution with degrees of freedom 5 and what? 66. Is that okay? And then the p-value is very small. It's less than, it has about 16 zeros before you get to the value 2. So it's quite close to 0. So what will be your decision? We reject H0. H0 in this case is that there is no difference between the averages, right? Is that okay? Which means there is what? A significant difference between what? The average count of course, you can see it over here. If you look at this, you cannot say that this is what? Not different from that one. These ones, they may be the same. So, any question on this? Any question on this? Okay, so that's it. If we want to use our F, we can also compute an F value for the degrees of freedom. So that will be KF, right? I have P is what? 0.95. Then I have DF1 to be what? 5. What about DF2? It's 66. So that is 2.35. Look at the F value. The F value is 34. It's greater than what we read from table. So what do? You reject the null hypothesis. So whichever one you use, you get the same answer. But the key thing, this does not answer our question. Our question was that which one is the best? So now we know that there are differences. So which means there will be someone which is high, others which are very low. The graph gives us an indication. Of course, we can rule out all these three, right? B, C, D, and E can be ruled out if we want the highest. What we don't know is between A, B, and F, which one is the highest? No, that's also descriptive. Remember, we said we don't use descriptive statistics to make a conclusive statement. So we are going to do a test again. So this test, we call it a post-hoc test. Post-hoc test. Post-hoc test. Or a multiple comparison. In some books, you see multiple comparison test. What is this test? It's simply a test that we perform after we have rejected a null hypothesis in an ANOVA, which means there are differences between the population. So then we want to see which ones are different. Is that okay? So that's what we do, the post-hoc test. There are several of them. There's 2K, there's Nanette, and what have you. Okay, but we'll just stay with the 2K test. Okay, so I'll just write something that we reject the null, we reject H naught, that is there are significant differences, right, between the counts, of insects killed by the sprays. Okay. Now the question is, so does we perform what? A post-hoc test. Perform a post-hoc test. Okay. Now the post-hoc test will help us to know which ones are smaller and which ones are what, like kills more of this. Okay. Now to do so, we use the 2K HSD. So you can check the help files for 2K. So all we need to, there are other, but all the argument we just need to pass through is our model, which is the model, the ANOVA model. So we just pass it through 2K. It's 0.95. So what I need to show you is how we are going to interpret this. So just pass our this in through the 2K, okay, and it's like this. So we did that, and this is our results. So you see there is this six sprays. So what is happening is that when you take A, you have to compare it with B, C, D, E, and F. Then you take B, you compare it with all A and so forth. That's why you have all that over there. So you see the first one, A compares with all of them. Remember, our aim is to get the one which is highest, right? Okay. So let's see. Here, the first one is the difference between B and A. The difference is positive. So what does it mean? It means B has a larger count than what? Than A. If we get negative, it's the other way around. Okay. Now, then the lower limit for this difference and the upper limit are this. Remember, if they are different, this interval will not enclose 0. Is that okay? If they are the same, then we expect it to include 0, right? Or if they are not significantly different, it will include 0. This one, does it include 0? The upper limit and the lower limit? Yes. So if you look at that, see A and B, they are not quite different. The box plot, you could see that. So look at the p-value, quite large. So this means that A and B are significantly not different. Is that okay? Then we move on to, even though B is, in the descriptive point of view, larger than what? Than A. But the difference is not statistically significant. We move on to A and C. A and C, the difference is quite large. Negative 12. What can you say about A and C? A is, yeah. So A kills more insects than what? Than C, than spray C. Now we have to check whether this difference is significant. It does not include 0. So what do you say? It is not significant. Are you sure? The difference is significant. Yes. In other words, it is significantly different from 0. It's negative 17 to negative 7. It does not include 0. It's far away from 0, which means the difference that we got, which is negative 12, is quite different from 0. Okay. Look at the p-value. The p-value is 0.0000. So what do? You reject H naught of equality. Okay. So this one, we can rule C out, right? Okay. If you look at A and D, similarly the same. We can rule D out. A and F, no, A and E, we can rule E out. So in other words, I am ruling all these out because they are odd, quite significantly different from A, and A is higher. So we can throw this one away. So we can then concentrate on A, B, and F. Is that okay? Is that okay? Because we want the one with the highest count of insects. Sure. So we have already considered A and B. We know that B is larger than A, or B is higher in terms of the count than A. What we don't know is B and F, right? So it's like I can rule A out now. Then I consider only what? B and F. So we go down and check B and F. B and F is here. So F minus B gives us positive, even though the difference is not significant. But we know that F is what? So you can see that A, B, and F, they are not significantly different. But in all, F kills more insects than all of them. You see, somebody was saying, can we say it's F? But that is descriptive. So if you take all this, even though they are not different from here. So, for example, if this is from a Chinese factory, and this is from maybe 1D, 1F factory, then government will say, well, because B is not significantly different from all of them, because we want to do promote made in Ghana goods, we will source all our sprays from here. So this is how you can use some of these things to make decisions. Okay, but if you are sourcing it from here, you are shortchanging yourself. Okay, because they don't kill the insects, as compared to these ones. So even though we want to promote our made in Ghana, it must be competitive to some of those outside. So please use the same analogy to check the data on the from the insurance. Okay, in the insurance data, we had automobile insurance claims. What you need to check is whether the states, the amount paid from each state is significantly different. We did a box plot, so you're going to do the box plot. You can color it. Okay, talk about the box plot, your initial things about it, and then you check whether you should either reject the null hypothesis or not. What I should caution you is that remember that ANOVA has what? Assumptions. One, that they come from a normal distribution with a constant variance, right? I have not checked for whether the variances are constant or not. Because if the variances are constant, there are other tests that we can use. Okay, like the Kruskal-Wallis. Okay, so all what we have done are purely parametric tests, but they are the non-parametric version. So we can do a Wilcoxon test for the T test that we did if the assumptions are not satisfied. Okay, in the ANOVA, we can use the Kruskal-Wallis test if the assumptions are not satisfied. So for example, if we want to check whether these ones, the variances are the same, so you use, I think, Bartlett. There's Bartlett test, right? Okay, so Bartlett test will give you the, not this one, but insect sprays, right? It will check whether the no, it has to be is it count, right? Count on spray. This one, I'm not so sure if it takes this, but let's see. Oh, okay, yeah, it did. Okay, so here I am checking whether the variances, remember that ANOVA test, the variances should be the same. So Bartlett test for what? Homogeneity of variances. Data by count, K is this, p-value. The p-value is small. So what this tells me is that the variances are not the same. So actually the ANOVA we did is not really the proper thing for us to do, because the variances are not the same. Is that okay? So what we need to do is a Kruskal-Wallis test for the insect sprays. And you can see it. You can see it from the plot. Can you say that the variation in this one is the same as F? No, the F is wide. This one is quite clamped together. So there are differences within the variances. So for such a data set, you don't use that. But of course, you can use Kruskal. You see, so Kruskal-Wallis test is there. You can use it. So these are big statistics. I don't want to reduce the class to a statistics one, but it is important that you know some of these things because it helps you in analyzing the data set. So please get yourself busy with the insurance data, which is within your field. Check whether you can say that the states, the averages of the claims within the states are the same. Whether the assumptions underlying ANOVAs are satisfied. You can report. So please let me get your work.